Thank you, Shani, for the nice introduction. Hi, guys. Good evening. So, yeah, let's directly jump into today's topic. So, basically, today I'm going to talk about one of the most latest topics in the generative AI domain. So, which is about agents and knowledge graphs. So, Um, so today we are gonna talk about basically couple of things. So we'll start with the retrieval augmented generation, one of the widely used techniques to interact with large language models, and then we'll move on to our main topics, which are agents and knowledge graphs, and then finally we'll put everything together and try to create something a bit interesting. Yeah. So so today I thought of creating a kind of a agentic conversational, basically conversational agent kind of thing, um, with Game of Thrones. I hope you all are fans of Game of Thrones, and let's see how we can create a chat agent with God. Cool. So we'll start with the most basic stuff. So first of all, I hope you all understand what is a large language model and how we can basically interact with. So I mean, just to give you a brief idea, uh, in very simple terms, LLM is a huge neural network which can predict the next word, right? Simply. So it was trained on huge amount of data and it has considerably complex neural network architecture. So given those two facts, it can, when we give a set of words, it can predict the most probable set of words. So that's basically what um, LLMs do, right? So the input text or the questions that we provide into the LLM is called prompt, right? And the response or the answer that we get from large language model is called the completion, right? And so we have certain techniques. I mean, I hope you all have experienced the scenarios where you don't get the expected response uh, from the LLM, right? So I mean, I hope you all have all had serious discussions with ChatGPT, of course. Sometimes you even forget, right? This is just an algorithm, and you start screaming at it, and you know things get worse. So I mean, how we can the first way to interact with LLM is how we can optimize the prompts to get the expected output, right? So there are certain scenarios, as I mentioned, where we don't get the expected output. So but we can do certain things to the prompt, and there are certain parameters that we can tweak to bias the LLM output or the response towards our intended output. So that the process is called prompt engineering, right? We have when it comes to prompt engineering, there are like huge amount of different techniques. For example, we can introduce persona, we can introduce instructions, adding more context, and so there are certain things called instruction tags for each LLM, and we have zero shot prompting, few shot prompting. We have like huge amount of techniques, and in terms of parameters, we have temperature, we have top P, top N, right? Greedy sampling, random sampling. There are certain parameters as well where we can control the LLM's behavior to a certain extent, and we can control the prompt that we provide into the LLM. But that's actually not enough to get the relevant output when we ask questions about specific things, right? For example, you have so let's say you are working on a financial industry and you have to you have to answer like uh, get certain answers related to your data, right? Or your specific processes, let's say. But most of the times, LLMs fail to do it. And but the thing is, it doesn't, stop generating answers. It generates something, but the thing is that the answers are not relevant, right? On the other hand, the answers, I mean, LLM provides answers very confidently, right? Confidently, but irrelevant answers. So that's called basically hallucination. Um, that happens basically due to lack of domain expert knowledge, right? So LLM is trained on, general set of data. Of course, it like those training data has covered most of the, general things, like in general. But when it comes to our specific use cases, LLMs might not have the, you know, required domain expertise. Or and the other thing is LLMs are we can't say LLMs are up to date, right? Their responses are, because I mean their knowledge restricts to their training data, right? So then what are we going to do? So first thing, we started with the simple prompt, and then we optimized the prompt and we did certain things to the parameters, and now still we are having this problem, right? We can't generate uh, relevant output from the LLM. So then what we can do? So the next step is called retrieval augmented generation. That's basically combining LLM's capability to generate an answers with our own data. So what we are doing actually in retrieval augmented generation, or simply RAG, is that we um, expose our data that we want to incorporate into our conversational or answers to the LLM. So LLMs can refer the data and get the relevant uh, answers for us, right? So that's basically retrieval augmented generation. So I mean, basically, simply let's talk about how RAG works. So let's go here, and the RAG basically consists of three processes. So one thing is called ingestion. So where we convert the data that we want. For example, let's say we have data in huge amount of PDFs in our organization. So we want to create a conversational something with that data. So then we have to do certain pre-processings, right? So we can, I mean, like generally the pre-processing steps are like chunking. We split the uh, data into certain smaller chunks, and then we create something called vector embeddings. I hope you all know these basic things. Vector embeddings means the vector representations of these text data, right? And then we are gonna store these data in a specific special data structure called index, right? The speciality in indexes are created in a way which makes easier retrievals, right? So when the embeddings or the data are in an index, it makes the LLM, the pipeline to make it easy to retrieve. So we have documents, we split them into chunks, and then we create their vector representations, store it create an index, and those indexes are stored in vector databases, right? I hope you all know the vector databases. We have ChromaDB, Pinecone, huge amount of vector databases, Qdrant, right? And now our data that we want to expose to the LLMs are in vector database. So then what happens is in the second part, I hope you all can see my cursor. So user asks a question, we call it user query from the LLM. And then what we do is the user query is also converted into this vector embeddings, right? So we have the vector representations of the data in the vector database, and when we get a user query, we can convert it into its vector form as well. And then we do certain intelligent search. We call it semantic search, similarity search, different names and different techniques to get the most relevant content out of that indexes or this data, right? Once we get, so that part is called the retrieval part. So this part is called the ingestion part, and getting or creating the vector embedding for the query and getting the most relevant content is called retrieval part. And then we pass usually top like n number of most relevant chunks to the LLM with the user query, and we generate an answer. That's called the generation part, right? Retrieval part, augmentation part, and the generation part. So this is a more detailed explanation about the RAG pipeline, as you can see. So we have documents, and we have like to convert the document chunks into its vector form. We use something called embedding models, and then we store them in the in a vector database, and we get the query. And again, we use embedding model to get the embeddings of the query, and then we do the similarity match or semantic match, and then we get the relevant context, and we pass all these things into the LLM to generate the final response, right? So this is basically the basic structure. So since retrieval augmented generation, this process can incorporate different types of data. Your data can be in a CSV, your data can be in an Excel file, PDF, Word document, maybe a website, or what else? Maybe a relational database, non-relational like NoSQL database, can be anything, right? So, I mean, therefore, we have to further optimize this process in order to get the best output, right? So how we can do it? So there are like three major ways of optimizing these RAG pipelines. So the first thing is called pre-retrieval optimization. So you can tweak uh, the chunks, how you generate the chunks and how you create the embeddings. So you can use a proper chunking strategy, or you can use a better embedding model likewise. And the second step is retrieval optimization, where we optimize the retrieval process. So instead of plain old similarity matches, you can use hybrid matches and more complex retrieval processes. And there are certain things for the augmentation part as well, right? After retrieval. So those things are called post retrieval optimization. We can use, so once we get the most relevant content from the vector database, we can rank those content again. We call it re-ranking, right? After getting the uh, retrieved context, we can again reorder, re-rank, and then um, filter out the junks and provide better retrieval content into the LLM. Likewise, you can improve the RAG pipelines. There are so many techniques, right? But so let's think about use case, right? So now we have this New Zealand tour in Sri Lanka these days, and so yeah, I thought of like, why don't we talk about cricket, with the LLM. Let's assume, so Sri Lankan Cricket Board has a detailed report about each player's performance for a couple of years. Let's say it's a detailed report and it's kind of a huge PDF, right? So we want to chat with that PDF, right? So we can ask different questions. So I want you to focus on like two different types of questions. So the first question is something like this. So it's very simple, straightforward. Name a ground Kusal Mendis played in 2024, right? So then if we create a rack pipeline with that PDF, so again, we are going through the process. So the PDF, the content in the PDF is broken down into different smaller chunks, and those chunks are converted into embeddings. So they are in the vector database. Now we are inserting, or we are feeding this query question into the rack pipeline. So this question will be, converted into its embeddings, and then we'll do a similarity match to get the most relevant content. So there will be uh, uh, several sentences or paragraphs about Kusal Mendis playing with this team in R prime the ground, or overs, or like something like that. Then the most relevant contents becomes those things, and they will be retrieved, and finally LLM will generate an answer like Kusal Mendis played in this ground and something like that, right? So one thing to notice is that in when we do the retrieval part, we compare each and every embedding, right? That means the text chunk with our question. So we get the question and we have the whole set of different text chunks in the vector database. Now we compare one by one, right? So that thing is called local semantic relationships. We with uh, so we compare the question with a single text chunk at a time, right? It could be paragraph, sentence, it doesn't matter, right? In the whole document, we compare we compare our question with a single sentence or single paragraph in the document, right? So we have a bit of problem. Let's go to the next question. Okay, now we have a now let's say this is Sanath Jayasuriya interacting with this rack pipeline. Now he wants to understand how does Kusal Mendis perform in low scoring matches on spinning pitches against top tier teams. So now this question involves different aspects. So we have to consider low scoring matches, and we have to consider spinning pitches and top tier teams, right? A single question, but different aspects. But for sure, all these content, all the content required to answer this question will be available, is available in that entire document, right? Entire document, that's for sure, right? But the thing is, our LLM guy, what he does is converting these questions into embedding form and compare this question with you know with text chunks one at a time. Okay, so we get the question and we get a single paragraph or sentence and compare. Okay, does this relatable? If not, no. But in order to properly answer to this question, that approach is not enough, I would say, because the thing is usual. So we say this approach, like the typical retrieval augmented generation approach, is called like vector RAG, right? Because we use just the vector representation. Vector RAG doesn't maintain or keep or persist the global context relationship, because we break down the entire document or the entire content into smaller chunks and then we isolate them, right? So I mean, we can't expect to get a proper answer for question 2 in an general uh, retrieval augmented generation pipeline. So then how do we improve this? And on the other hand, other than this thing, the question 2 involves reasoning as well. So whoever the person is going to answer to this question has to think about certain aspects and combine certain things, get data from different different places in the document and combine them, something like that, right? So let's see how we can improve this situation. So one aspect is we can improve the data representation in order to get the answer, right? Because now the data is kind of isolated in embeddings. They are not interconnected. The content or the entity relationships in the PDF are not preserved in the embeddings, right? So we have to find a better data structure to represent the PDF so that we can answer to that complex question. That's one. And the second thing is, so we have to add some reasoning as well, because these kind of questions involve reasoning. So you can't just get the data and throw it out as the answer. So you have to do certain reasoning and then formulate the answer. So there are two aspects, right? Now we get to the knowledge graph. So why we get to the knowledge graph? So the first aspect, we have to come up with a proper data structure to represent that PDF data, right? Because at the end, it's not just the text data. So there are certain relationships that are represented in that PDF. So that's why we go to the knowledge graph. So knowledge graph is nothing but the data structure which represent the entities and their relationships, right, together. So in knowledge graph, we have certain entities which represent, it could be a person, it could be a concept, it could be an object, like anything. We can define how the knowledge graph should be created, right? And then we have certain relationships. How we can connect each nodes. So we have the better representation of data in knowledge graphs. And the most important thing is we can preserve global semantic relationships. To answer to that kind of complex questions, we have to have that global semantic relationships, right? So we'll dig deeper into knowledge graphs for a bit and see how they works, right? So basically, I mean, knowledge graph itself is a huge domain area, right? So most of the things that we see in the internet represent a knowledge graph. For example, Google knowledge base is a knowledge graph. We have Wikipedia. We have Facebook. What do you call it? Facebook. Even the friend network or the Facebook data knowledge base is also a knowledge graph. And we have Instagram. Most of the social media platforms use this data structure, right? So simply, um, and if you want to learn more about the knowledge graph, I guess you should start with graph theory concepts, right? Just saying. So if we go to the basics, knowledge graph is created from nodes, edges, and relationships. So nodes are the entities, right here. So we have certain nodes which represent entities, could be person, object, concept, anything. And then we have edges, which connects the nodes, right? Could be two nodes or multiple nodes. And there are relationships means, so there can be different types to edges, right? So these entities can be connected in different ways or different aspects. So those things represent relationships. And yeah, when we talk about knowledge graphs, so we get to entities and relationships. That's basic. And when we create knowledge graph, we can from the unstructured data, right? For example, text or any other things, we have to use schemas. So we can define what kind of knowledge graph that we want, right? So that's called basically schemas, and we have to consider something called query language. So knowledge graph is like, you can consider it as a, let's say, a database or something. So you have to uh, uh, maybe insert entities or relationships into the knowledge graph. You can retrieve certain, content, basically subgraphs, certain nodes, certain relationships. Basically, you have to query, right? So for those things, you have to use query languages. So one of the most um, widely used query languages these days are called Cypher. Cypher is the query language for Neo4j. So Neo4j is a graph database and a graph engine. So we are going to use Neo4j today. And so if you want to query a Neo4j knowledge graph, you can use Cypher. It's just a query language. There are a bunch of others as well. Right. So then, yeah, we understand, okay, we can represent the, let's say, the cricket content in a knowledge graph, right? So now there are different types of knowledge graphs as well. Huge, like there are a bunch of different types. And one of these special types of knowledge graph is called property graphs. So I want you to focus a bit on property graphs today. So usually knowledge graphs represent certain amount of information, and it has certain restrictions when we create knowledge graphs, right? So if you want to create a knowledge graph, you have to have a schema, right? Proper structure. But property graph is an improved version of knowledge graphs, right? Which have certain properties. So one thing is, apart from the main concept that is stored uh, in the node, you can store certain metadata, or we call them properties, right? For example, if let's say we are representing a person in a node, in a knowledge graph, but if we created a property graph, then we can add certain properties to the node, like name, uh, birth year, certain properties, right? And we can do the same thing for the relationships or the edges as well. So we can add properties to the relationships or edges. That means our knowledge graph or the property graph becomes um, rich in information than knowledge graph, typical knowledge graph. On the other hand, the retrieval processes and how you can, manipulate the knowledge graph is comparatively simple, right? And one of the most important features that we have um, with property graph is that it can store the vector embeddings of this content as well, right? So you have knowledge graph and you have the vector embedding. That means, you can remember the vector embedding that we created for the cricket thing, right? So that means we can again store the vector representation as well. So we have the graph representation, and in the property graph we have the vector representation as well. So that means we can do hybrid search. So usually how we retrieve the content from knowledge graph is using graph based retrieval methods, right? And if you are using a property graph, you can combine the graph retrieval approaches with the vector retrieval or the embedding based retrieval approaches and make a better retrieval outputs. So those things are some of the advantages of property graphs, right? Okay, I mean, so when we combine retrieval augmented generation with a graph, we get something called graph RAG, right? Knowledge retrieval augmented generation on graphs. It could be knowledge or property, right? So this the initial concept was published by Microsoft. They introduced this graph RAG concept. So basically, this is how it does. So we have the source documents, we do the extraction and chunking, similar to vector embeddings, and then we do certain, this is important, summarization, right? So because we use certain summarization to traverse through the, graph nodes and yeah, different branches, right? And after that, we are doing something called community detection. We detect the entities, right? We detect the entities and we connect entities and then we group entities. So those groups of entities are called communities, right? So then we can, so it's like so when we have a graph, it's like a subgraph, right? A branch of the graph. So then we have communities. So then we do um, community summarization. So you can summarize an entire set of nodes or the set of, subgraph and represent use a summary to represent that subgraph for set of nodes. And then in the query time, you get the very similar. You get the answer, query, and then you match. Basically, do a hybrid search and get the answer. Right. This is just a basic outline. You can read the graph rag paper from Microsoft. It's really nice. The approach is really nice. And now I guess they have created uh, their own Python package as well. You can, I mean, you don't have to implement things from scratch. You can just use the package and create graph rag pipelines. So yeah, that option is also there with certain limitations. Right. So now we discuss about one aspect, how we can improve retrieval augmented generation. One thing is like that's basically representing the data in a better data structure, right? So the second thing is we talk about we need to have reasoning as well when we get the complex questions. So adding reasonings means so you have to think about agents, right? LLM based agents. So how we can improve reasoning is by incorporating the RAG pipeline with agents. So we call it Agentic RAG, right? Let's talk about LLM agents for a bit. So I hope you all have worked with some kind of agents before. It could be travel agent, banking agent, literally anything, any kind of agent. So agent is a person or a system that does something for us, does a specific set of things for us, right? So based on the instructions or the functionality that we have given to the agent can reason out certain things and make certain decisions, and uh, agents can do something for us, right? So likewise, LLM agents are just systems which are built around LLMs, right? By incorporating certain components which can do certain things autonomously, right? So if you can see this image here, so in agent we have certain components. So we have the foundation model, basically the LLM, right? And we have certain tools. We provide certain um, tools to the LLM. Right? It could be web APIs to search, web. It could be certain applications, or it could be anything, any kind of tool, maybe some Lambda functions or anything, right? And then we have another component called memory, right? You can add memory to the agent by incorporating a database. It could be vector database, maybe a cache or anything, right? And the most important thing is, so this action part is is that you can incorporate reasoning frameworks into the agents, right? So we have certain reasoning frameworks in generative AI that we can incorporate with LLMs. So we'll get to the reasoning frameworks a bit later, right? So it defines a certain way of thinking or reasoning. So when we incorporate that with LLM, so LLM starts to, reason out within that framework, right? So there we have like bunch of different frameworks, um, um, and based on the functionality, we have a bunch of different agents as well. So we have conversational agents, workflow agents, function calling agents. For example, um, conversational agents are very common type of agents, and the workflow agents are something like if you are doing if you're working on a large organization and you want to automate certain processes, right? And those kind of uh, in those kind of scenarios, we can use workflow agents. And function calling agents are we can provide agents with certain functions, like certain functions, and ask it to pick a function based on the based on the requirement and execute something. That's that. And there are bunch like different other agents type as well. So yeah. So when we think about reasoning frameworks, we have bunch of different reasoning types, right? So these are one of the most popular reasoning frameworks, right? We have called React, reasoning and action. We have chain of thoughts, and we have another called tree of thoughts, toolmaker, meta reasoning. So basically meta reasoning is you can make LLMs to reason on top of their decisions. So it takes a decision and it reason out again on top of it, and likewise until it's get better response or a structure, the reasoning happens. And we have another reasoning framework called active prompting. So active prompting is very widely used in those coding assistants. Um, for example, GitHub Copilot and other coding assistants heavily use this active prompting reasoning frameworks. And we have reflections, bunch of different reasoning frameworks. So agentic RAG basically means, so we have the agent, right? And then what we do is we incorporate the retrieval-augmented generation pipeline as a tool into the agent. So so we get a question, and agent analyze the question and reason out things. Okay, whether I can answer to this question with the knowledge I have. And when the reasoning happens, it figured out, okay, I don't have the required information, and then I have to use some kind of a tool, right? So then it looks for the tools that we provide, right? So we have a different tool sets, and we can expose our RAG pipeline as a tool, right? We can expose our knowledge bases, knowledge sources, vector database, graph database, and other RAG pipelines, so that the agents can use these RAG pipelines to get the required context and then answer the question. So that's what basically the agentic RAG. So you have the agent and you expose the RAG pipeline which has the domain expertise to the agent, so that the agent can reason out and get the expected answer, right? So that's agentic RAG. So now we discussed about two aspects to improve that RAG pipeline. One thing is we can incorporate knowledge graphs to have a better data structure. And the second thing is we can combine RAG with agents so that the RAG pipeline has the reasoning component as well. So yeah, basically knowledge graph improved retrieval and agents improved reasoning, right? So this agentic RAG with knowledge graph basically provide two things. One thing is complex reasoning and um globally enriched information. That means we, by knowledge graphs, we preserve that global um, um, contextual relationships, right? So, I mean, this is basically the solution architecture that I was planning to do. But let's focus on this graph RAG agent, and you can simply deploy the RAG agent in AWS Lambda. It's very easy. You can just create a Lambda and put the handler, uh, put the agent inside the handler. And for this, I'm gonna use two types of models: AWS Bedrock, the models in AWS Bedrock, and OpenAI, right? And for the graph database, we have Neo4j. Okay, so these are the basically the tools, and so and our main framework for this task is Llama Index. So we have huge amount of agentic and generative AI frameworks like Llama Index, LangChain, LangGraph. We have a huge amount of frameworks blooming these days. So you have to carefully pick the appropriate framework for for your use case, because each framework has its own pros and cons. All right, let's do some coding. I prepared a small notebook, even though I don't recommend to demonstrate things in notebooks, but yeah, with the time I guess you have to use a notebook. Okay, so before that I have to show this one. So this is Neo4j Aura. So this is completely free. You can just Google search Neo4j and create an account, and so this will be our um, big sorry, graph database, right? So I have one instance running, and I can go to here, and you guys can see my yeah, okay, cool. So I'm gonna connect to the database. So we have a couple of things. So query means you can use this space to query your graph database. And we have something called explore. So you can visualize the graph, knowledge graph, or the property graph in this section. So I guess I don't have any graphs at the moment. Yeah, I don't have any graphs. Okay. And so if you want to clear, so I mean, since if you are experimenting, I recommend you to use this free version. And if you are using the free version, you can for different use cases, you can clean the database out. So you can simply use so these are cipher queries. So I'm just can simply use match n and detach, delete n this query to delete the proper existing property graphs. Yeah, I don't have anything here, so it returns nothing. Okay, let's go to the code. So um yeah, for this, the major framework is Llama Index. So these are the basically the modules that I have imported. I'll walk you through the process, right? So for this, I'm planning to use three types of models. First type of model is OpenAI embedding models to create the embeddings, so the um, vector representations of our text chunks. And we have Bedrock, so we can use different LLMs available in AWS Bedrock, and then we can um, use the OpenAI models available in OpenAI, right? So I have you know inserted, or I'm loading all these required environmental variables from this .env file, right? Simple. So I'm going to use for Neo4j. So we need to use Neo4j URI, username, password, and database. All of these things you can get from the Neo4j account. And we have OpenAI key. And for Bedrock, we have these credentials. So here I'm defining the Bedrock models. So for this one, I'm going to use the Anthropic Claude 3.5 Sonnet using Bedrock, right? And we have OpenAI LLM as well. So I'm going to use GPT 3.5 Turbo, and you can use GPT-4 as well. Doesn't matter. So let me import the packages, and we can get the environment variables. Now so here I'm gonna use the Neo4j property graph store. This is a package available in the Llama index that you can map the property graph store into your property graph database, or the graph database in Neo4j. So now for this thing, so basically, as I mentioned earlier at the beginning, what I'm going to do is, so we are going to create a knowledge graph from Game of Thrones, right? So I have a summary that I got from I don't know, a website. This is a very, simple summary of Game of Thrones, because I can't use the entire books, right? Then I have to spend like a huge amount of money. So this is just a summarized version of Game of Thrones, which represents certain characters, certain incidents, basically certain incidents. So this is the text that I'm going to use. And first thing first, so we are going to import the document, and we are going to create using simple directory reader, right? So in Llama Index, we have huge amount of data loaders, right? You can ingest data from different sources into Llama Index pipelines, like from CSVs, PDFs, pretty much from anything actually, right? And then you do the sentence splitter. So the thing is, so I'm gonna create two tools. One thing is the knowledge graph, and I'm going to create a vector database as well, the typical RAG pipeline. So we have a typical RAG pipeline, and we have the knowledge graph based RAG pipeline. So we'll put them together with the agent, so that when we ask a question, agent can pick, okay, what is the tool I'm going to use to answer this question, right? So if that, you get the idea, right? If we have a general thing, then we can get something from the vector database, and if you have specific question, then you can get things from the graph database. For the vector database, I'm going to use this sentence splitter, and so we are creating nodes from the documents. Nodes basically represent the chunks of documents, and you can simply, okay, now we have created 21 nodes, right? So nodes represent the document chunks with their metadata, right? And now for the property graph, so we don't have to have a schema for the property graphs, but if you want your property graph to be well structured, you can definitely use this kind of schema. So you can define the entities. So I have person, house, place, role, and event. And I have the relations. Belongs to, located in, family, investigated, participated in, occupies, betrayed. So these things have been generated based on the story, right? And I have the valid relationships as well. Person belongs to house, person, family of person, likewise. And to extract these entities and relationships, I'm going to use something called schema LLM path extractor. And there are certain other extractors as well, like implicit path extractors, which is the simplest form of these entities and paths extraction. But in this case, I'm going to use schema LLM path extractor, and I'm going to use, for now, I'm going to use OpenAI LLM, because the last time I experiment, OpenAI embeddings didn't work well with um, Bedrock models. So I can't use Bedrock embedding models at the moment. So stick to OpenAI LLMs. And so these are possible entities, possible relations, and validation schema, and we can execute. Okay, now we are creating the two indexes. So this is for the property graph, and this is for the vector database, right? So we pass the embedding model, knowledge graph extractor, that means this one, right? And we have passed the property graph store as well, and the documents. So everything put together, we can create the property graph index and the summary index as well. So it might takes a bit of time. Let's see. Okay. It's generating and storing the knowledge graph in our Neo4j. Okay, we are done. So let me go here. Now we didn't have any, knowledge graph before. So let me go to here, explore. And so I'm gonna create a different, refreshing my perspective. And so you can go here and you can simply check, show me a graph. Let's see, there we go. So as you can see, we have created the knowledge graph from the, very brief explanation that we had in the what do you call it, in that um, our input text. So as you can see, we have entity called Jon Snow, we have entity called Battle of Winterfall, and the relationship, it has properly identified the relationships participated in, right? And we have, what are the, see, Starks have been belongs to the Stark family, right? Winterfall located, so if you can let me zoom in, Winterfall located in north. See, it's nice. So I mean, this is without any optimization or anything. You can again apply to, apply certain optimizations as well for this one. Yeah, so this is our knowledge graph for the agent. Let me go back to the code. So we have the knowledge graph and the summary index. That means the vector database, vector index. And I'm gonna convert, so after creating indexes, so we need to answer questions, ask questions from this graph and the vector database, right? So for that, we can use something called query engines. We can convert the indexes into query engines. Query engine means you can simply ask questions from it, right? So and I have created a retriever as well, just to show you how things retrieve for the knowledge graph. So let's test the retrieve, test the retrieve and query engine. So I have the retriever. So let's type a question and see. Let's say, who is, no, something like that. And here I'm getting the the most relevant nodes from the graph to answer this question, right? Here I got certain nodes which with lot of information, right? And C belongs to Jon Snow, belongs to what? Belongs to, oh, it's very lengthy. Stark. And I don't know, betrayed. Jon Snow betrayed someone. Yeah, Lannister. So that this is purely based on the description available in this text. Okay, I didn't go through the text because and therefore I can't validate what is inside, but the knowledge graph has been created according to what's inside here. Maybe I'll share the code with you so that you guys can go through it and maybe try with your own data kind of thing. Okay, never mind. So we have so this is the retriever. Now let's test the graph query engine. Let's ask a question. So the question is like, who participated in the Battle of Winterfell? Because I mean, there is no a proper, a really nice sentence in this text. I validated that which describes, okay, these people participated in the Battle of Winterfell. But so now so we have the Battle of Winterfell. So the graph will traverse through this thing and try to connect the people who participated here. So let's try. Okay. So this is just the retriever, okay? Query engine. We haven't done any reasoning here. So here it says Jon Snow, the forces of the living, and the Night King and his army participated in the Battle of Winterfell. It's a valid answer, right? So it's good. Okay, now this is just retrieval. So let's plug the agent part as well. So before creating the agent, we have to convert these indexes or the query engines into tools. If you can remember, I told earlier that we have to expose these RAG pipeline as tools. So I have in Llama Index, we have tool called query engine tool. So I have two query engine tools. One is for uh, property graph query engine. So I have a name and the description. I say, so from this query engine tool, provide information about people, incidents, and other relationships. So let's, yeah, it's valid, and use a detailed plain text question as input to the tool. So you can define certain restrictions and descriptions to the tool. And we have the second query engine tool. This is for the tip, the ordinary like RAG pipeline. So Game of Thrones summary tool, provide summary related to Game of Thrones, useful for summarization questions. But you can alter these descriptions. So I'm going to create the query engines. So now I'm creating the agents. For this, I have used the React agent, reasoning and action. So you can use the other agents as well. So here in this agent, I want it to reason out and do the reasoning and make certain decisions. So I'm going to create the okay, right. And I have one question. This one. Let's try this question. Give me a summary about Jon Snow. Let's see how the agent works. Okay. Okay. There are steps. Okay. Okay. Nice. So we have the thought process as well, right? So thought means how the LLM or the agent thinks. So it thinks the current language of the user is English. I need to use a tool to help me answer this question. Okay. Now it's going to use a tool. Action, Game of Thrones summary tool. So it has chosen the summary tool to answer this question because we are asking a summary. Now the input, summary about Jon Snow. And now it has observed the response from the summary tool. So the response is this: Jon Snow, the legitimate son of Ned Stark, blah blah blah. And yeah, we have a description coming from the vector database, right? Validate whether it's correct. I'm not sure. Yeah, and now the agent thinks again, okay, I can answer without using any more tools. Okay, I'll use the user's language to answer. Reasonable. Now the final answer is Jon Snow and the proper summary about that. So let's ask a specific question about a specific person or some incident. Or maybe we can use the same question here. Who participated in the Battle of Interval? Because it's a question about specific event. Let's see how it gets the content. So I'm going to execute this one again. Okay, it's thinking. Okay. That's weird. Let's execute again. Oh, there it is. There you go. Again, user is asking it's thinking. User is asking for a list of characters who participated in the Battle of Interfell. So it's going to use an action, Game of Thrones property graph tool. Now the action input is list of characters who participated in the Battle of Interfell. And it has observed the response from the property graph. Jon Snow, Daenerys, Arya Stark, Sansa Stark, blah, blah, blah. And it again thinks, okay, I can answer without using any more tools. So it's going to create its final answer as this. As you can see, so the React agent thinks and pick the correct tool to answer to our question. So in this way, we cannot we can answer to complex questions based on the data available here, and make it a really nice agent, I guess. And we will share this code base with you so that you guys can try with different different scenarios. I don't think this chunk of data or text is the proper representation of Game of Thrones, but you can maybe try with different chunking strategies, or like try to summarize the book by on your own, and then feed this and see something like that. So that's how we create agentic RAG with knowledge graph using Llama Index. All right, I guess that's pretty much it from my end, and so it's time for questions. If you have any questions, feel free to maybe raise your hands and ask the questions, or you can put them in the chat as well. Yep.
Thank you so much, Gihan. Did you rewatch all of Game of Thrones to get ready for this?
Not really, but I'm a
Okay,
fan of. Yeah.
awesome. We've got some questions coming in. So number one, in RAG, felt like LLM is only used for formatting and organizing the words for a meaningful display, since memory and content are in vector DB. Edge models might work as well for RAG for a cost and optimized pipeline. Or does an extensive LLM make it easier for reasoning framework?
Can you repeat the? Okay, let me see. All right. In RAG, felt like LLM is only used for formatting and organizing the words for a meaningful display, since memory and content are in vector DB. Edge models might work as well for RAG for a cost optimize pipeline. Or does an extensive LLM makes easier reasoning framework? I guess, yeah. I mean, in RAG pipeline, LLM it's not only used for formatting and organizing the words. I mean, that's one of the part. Like, I mean, for if we think about this kind of example, that's, I mean, you might feel like this is the scenario. Okay, LLM doesn't do much, but let's say you are plugging a database, right? Then the LLM has a huge amount of responsibilities in generating the proper response. So I mean, that means I mean, it's not only formatting the output, but you have certain reasoning. I mean, without agent, you have to do certain reasoning using an LLM. And if you are using, edge models or anything, I mean, I think the reasoning parts, you have to compromise the reasoning, and then it will be more like mostly kind of similarity thing. But based on the so there are certain scenarios that we only retrieve something, we don't do the generation part. That means the completion part, right? But that depends on the use case actually. Isn't giving setting property graph schemas from our end limiting the possible prompts from user? Exactly, that's true. Yeah. So I mean, I created the schema because I wanted specific set of behaviors from the property graph. But you can just ignore the schemas and let the LLM to pick the entities and relationships and create the property graph. That way it will, it will be very comprehensive. Like it will create comparatively lot of nodes and relationships, because LLM can capture different aspects, right? So here I'm limiting the LLM to focus on specific aspects. That's very true actually. That depends on the use case again, Samir. Nice questions. And we have one more: how we can use above method on a quite large CSV file like 9,000 rows. Okay, I mean, for this kind of thing, I don't think a single agent or a single rack pipeline might work, because uh, the thing is, if you are like here you're talking about quite large CSV files like 9,000 rows, right? Then you have huge amount of text data, and when we are feeding into the embedding and stuff, you have, I mean, one major aspect is cost and the computation. So what I'm suggesting is you can build a pipeline. Okay, first you get the text, and then you can do something like named entity recognition kind of thing, and then you reduce the amount of information gradually by preserving the most important content, and then you can use the final set of extractions to create the knowledge graph, and to create the knowledge graph and RAG pipelines. Because that's true. I mean when we apply these concepts into production ready environment, I mean, we have to scale up things as well, right? So that's basically one of my suggestions to do it. Because most probably, in, let's say you have 9,000 rows, even a single column with, you know with information which are not relevant to this thing might add huge amount of cost and computational power as well. So we don't have, I think we have to do set of pre-processings and address this thing as a pipeline, not just a single RAG component or an agent.
Amazing. Do we have any more questions today? Oh, right. Let me see if I can. Beautiful. Manit, if you want to unmute yourself, you can ask a question or you can pop it in the chat. Maybe try and pop it in the chat then. Oh, we've got some new questions. Sorry, just trying to figure out the mics, guys. Does anyone have any questions they want to pop in the chat? Can we have all of the material you used here.
Yeah, sure, sure. I'll share the code base, and I'll share some resources, really nice resources to learn about knowledge graphs and agentic RAG. Yeah,
Also, this entire session has been recorded today and it will be uploaded onto our YouTube channel so you can check it out again and again and again. All right. Do we have any more questions, guys, before we wrap up for for today? All right. If you have any questions, please feel free to reach out to Gihan. I've tagged him on our LinkedIn posts for this session, and I'm sure he'd be happy to give you some answers. This entire session was recorded and it will be uploaded onto our YouTube channel next week sometime. And we will be posting more details about our next speakers. But thank you to everyone who joined. Have a lovely evening, and we'll see you next time. Thanks, Gihan.
thanks, Lulu. See you guys. Thank you so much for joining.